Assalamualaikum warahmatullahi wabarakatuh and a very good day. I am Nuraini binti Muhammad Noor. Will be presenting my work entitled Molarity Control KOH Activation of Sugarcane Bagasse Derived Carbon for Energy Storage Application. Okay, this is my presentation outline. I will begin my presentation with some introduction including a basic overview about this work, problem statement and also research objective, and then I will move to the research methodologies, moving to result and discussion, and finally I will end my presentation with conclusion and some recommendation. Moving on to the introduction. First of all, what is activated carbon? So activated carbon has a special properties such as rich in carbon, highly potential, high efficient, and usually it produced by carbonization or pyrolysis process. There are few types of pyrolysis process, which are fast pyrolysis, high temperature pyrolysis, and also slow pyrolysis, where among these three, slow pyrolysis produce the highest percentage of carbon. Activated carbon has been widely used for many applications such as water and wastewater treatment. It also has been used in air purification and gas treatment, environmental and sustainability uses, and it also has been used in energy storage and electrochemical devices such as supercapacitor electrodes, battery electrode additive, energy storage from renewable sources, and also fast charge discharge application. What is energy storage and electrochemical devices? So it is basically a device that capturing energy when it is available. It also can store energy for later use. It balance energy supply and demand. It improves reliability and efficiency, and it also supports renewable energy system. So there are many types of energy storage and electrochemical devices such as batteries, supercapacitors, capacitors, superconducting magnetic storage, and etc. So what are the main components of these devices? It must have electrolytes, separator, current collector, and also electrodes. In this work, we will highlight on the electrodes. For the electrodes, there are few types of materials that being used in order to produce the electrode. For example, conducting polymers, metal oxide, and also carbon-based material. Among all of these electrode material, there are few limitations that can be highlighted. First of all, it's on its sustainability, where conventional electrode materials rely on non-renewable resources, which raise concern over long-term availability. It also involves complex and energy-intensive fabrication processes, which leading to higher costs, and it also gave environmental impact where its processing routes raises environmental and sustainability concerns. So the solution of these limitations are using the carbon electrode material. So what are the advantages of using carbon electrode materials? It has high electrical conductivity, it has structural and chemical stability. However, among these advantages, it also have limited ion accessible in the active surface area. So then, that's why we come up with biomass derived activated carbon, which it is tunable microstructure and also low cost and sustainable. So in this work, we choose to use sugarcane bagasse as it is available abundantly. It has high carbon content suitable for porous carbon material formation. In sugarcane bagasse, it also has anionic material. Sugarcane bagasse also have three main components, which are cellulose, hemicellulose, and also lignin, and it also consists of negative charge. Next, we proceed with the problem statements and also the research objective. We are aware that carbon electrode material has high surface area and porosity. It also has tunable microstructure upon processing, and it also have low cost and sustainable. But the understanding of how potassium hydroxide molarity alone affects the microstructure and electrochemical behavior of biomass derived activated carbon under controlled carbonization conditions is still limited. Hence, in this work, we aim to prepare activated carbon from sugarcane bagasse using different KOH molarities, and we will examine how the KOH molarity influences the pore development, structural disorder, and also interlayer spacing. And finally, we will evaluate the resulting electrochemical behavior under fixed pyrolysis condition. So by the end of this work, we are expecting to clarify the role of KOH molarity in tailoring the microstructure and electrochemical behavior of biomass-derived activated carbon under control condition while promoting sugarcane bagasse as a sustainable electrode precursor. Moving to its methodology, so basically this work have 3 stages, starting with preliminary stage where we collect all the biomass, doing the washing and grinding, and in stage 2 where we do the chemical activation and pyrolysis process. In this stage, we only varies the molarity of KOH, and then we do the structural and elemental analysis, namely SRD, FTIR, and also SEM. And finally, in stage number 3, we did the electrode preparation for the electrochemical study where we have the linear sweep voltammetry, and we will finally find the optimized KOH molarity for this electrode material. Next is its result and the discussions. So for preliminary stage, as we can see here in figure 1A, it is a TGA analysis for sugarcane bagasse. So from the figure, it shows that sugarcane bagasse have 3 main mass loss stages. So its moisture will be removed below the temperature of 200 degrees Celsius, followed by the decomposition of hemicellulose and cellulose between 230 degrees to 375 degrees Celsius. And then the gradual lignin decomposition happens up to approximately 450 degrees Celsius, and then we can observe that minimal mass loss beyond approximately 500 degrees Celsius, which support that the selection of 650 degrees Celsius as a constant pyrolysis temperature for this work. Okay, as we can see in figure 1B, the SEM image of raw sugarcane bagasse. So from here we can see that there are fibrous structure with relatively smooth surfaces and limited visible porosity that consisting of elongated fiber strands and pith region with only minor inherent micropores. Okay, in stage number 2, we did the chemical activation and also the pyrolysis process, and we observe again its SEM. So from here we can see that at 0.4 mol KOH, only limited pore development is observed, and it is relatively compact surface. When we increase the molarity of KOH to 0.8, we can observe that it's increasing in surface roughness and visible pore formation. And finally, when we furthermore increase we can observe highly developed interconnected porous structure with thinner pore walls. So from this, we can say that increasing KOH molarity clearly enhances pore density and the porosity of activated carbon. And from the FTIR, we can observe that as the molarity of KOH increases, we can see that the peaks also shifted. It indicates that it increased its surface functionalization. Then at the same time, it indicates that enhanced chemical activation and also surface modification. Figure number 4, XRD for sugarcane bagasse activated carbon. So we can see a broad diffraction peaks which indicate predominantly amorphous or turbostratic carbon, 30 degree. And by increasing the molarity of potassium hydroxide, we can say that it reduces the graphitic order and also increases the structural disorder. So from the SRD study, we calculated the interplanar spacing of the carbon that is presented in table 1. So as we can see here, as we increase the molarity of KOH, the d-spacing of the carbon increases, where at 1.2 mol KOH, the d-spacing of the carbon is 2.96 angstrom. At the final stage, we did the electrochemical study where we run a linear sweep voltammetry of sugarcane bagasse activated carbon. So as we can see from the LSV here, increasing the KOH molarity results in higher current response. So we can see here at higher molarity of KOH, the higher current response can be observed, which indicates that the highest absolute current and also showing that it has a pseudo capacitive like behavior. And from here we can also observe that for the lower molarity samples, samples, it show more resistive behavior, and improved electrochemical response correlates with enhanced porosity and enlarged interlayer spacing. This is in agreement with our previous analysis done in the previous stage, which is XRD, where we have the highest D spacing, is also referring to sample that produce using 1.2 mol KOH. Last but not least, the conclusion and recommendations. So from this work, we can conclude that the activated carbon was successfully produced from sugarcane bagasse via KOH chemical activation. So from here, we also found that KOH molarity significantly influences spore development, structural disorder, and interlayer spacing at fixed pyrolysis temperature. Increasing KOH molarity enhances porosity and amorphous carbon structure, improving electrolyte accessibility. The 1.2 mol KOH sample has the most developed porous morphology, largest interlayer spacing, and also pseudo-capacity electrochemical behavior. Finally, sugarcane bagasse is confirmed as a low-cost and sustainable precursor for carbon-based energy storage electrodes. As a recommendation, we can perform additional electrochemical tests to fully evaluate the capacitive performance, investigate other activation parameters, evaluate electrode performance in full cell or supercapacitor device configurations, and also explore surface functionalization or doping to further enhance electrochemical behavior. And finally, the main contribution of this work is the systematic clarification of potassium hydroxide activation molarity as a key parameter governing the structural and electrochemical properties of sugarcane bagasse derived activated carbon under controlled carbonization condition. That's all from me. Thank you.